A little bit because I understand I'm talking too fast, but let us try to slow down. Reactor effluent air cooler corrosion, this is one of the main problems in refineries, and it happens in hydrotreaters and hydrocrackers. The effluent from the reactor goes through heat exchangers, and finally you end up in the air cooler. And the air cooler, you start depositing ammonium bisulfides and ammonium chlorides, and to avoid fouling, water injection is made to get rid of this fouling of ammonium salts. So you have ammonium sulfides and chlorides, and you have water. So you have the stream, very corrosive stream is formed in this cooler. And there are, if you have high velocity and high H2S content, because this stream has a lot of H2S, you have the environment to cause severe corrosion, and disaster. A lot of fires happen from this air cooler. There is an API document was made maybe 2 or 3 years ago, which how to design these air coolers, how to select materials, material fabrication, how to operate this air cooler, the inspection techniques for that to control this problem. So this is an API document which is very useful to guide for. Also, there are proprietary data which only for sponsors. Unluckily, we are not members of that group, but it also gives guidelines how to handle this problem. But for us, we look at the hydrogen sulfide partial pressure, ammonia partial pressure, and multiply the mole fraction. We get some factor, they call it peel factor. Give us some guide. Where are we? Can we use carbon steel, or we have to use some alloy, like alloy alloy? So it is challenging. And then also the piping design is very critical to ensure that the flow is equally distributed among air cooler banks and eventually in each tube. Water injection is very critical in controlling this corrosion, and you have to ensure that the water you inject is equally distributed into the banks and the individual tubes. So this is the background of it. You can use carbon steel if the conditions are not so severe. Otherwise, many people use now Incloy 825, or some people use duplex stainless steel. But if you don't weld it properly, you end up with cracking. And I have experience with the duplex air cooler, which failed after 1 week, cracked after 1 week of operation. It went through in 1 week, and we have to scrap it and buy new ones and shut down, a big loss. So the corrosion here is due to ammonium bisulfide and ammonium chlorides, and they act as you inject water to remove them, but they create some corrosive environment. These are very old data on ammonium bisulfide deposition, as to when it should deposit. And this is the temperature and the ammonium concentration. I think if you are below this curve, you are depositing. If you are above this curve, it is in the vapor phase. The same thing for ammonia, for chloride. The chloride dew point is much higher than the ammonium bisulfide. So ammonium chloride start first, especially even the upstream this heat exchanger. The ammonium chloride corrosion happen, but also it happens in the air cooler as well as the ammonium bisulfide. Okay. Now we go to low temperature. As I mentioned before, low temperature, you lose ductility with low temperature. Up. And below 20 degrees minimum design temperature, the steel should be careful using carbon steel because it loses ductility. And each equipment now should have a minimum design metal temperature, we call it minimum MDMT. And it is required per code for any pressure item, piping, or equipment. And if you know the minimum design temperature, then you start playing and find what best material to use. Generally, below -20 F minimum design temperature, you start using low temperature carbon steel, which means carbon steel which have been impact tested to make sure it is tough enough at the minimum design temperature. The critical thing in this issue is to decide what is the minimum design metal temperature. And the minimum design temperature is decided based on operating conditions, ambient conditions. For example, if you are in Alaska or in Canada, North Canada, the temperature is below like -45 C or -50, then you have to design for that, because when you start up, you have low temperature unless you have some heat tracing or precaution to avoid starting up with cold conditions. You have to consider offset conditions, because sometimes offset condition can create low temperatures. And if you are not designed for these conditions, you might end up with cracking. Some environments like LPGs, and they have auto refrigeration, and when it expands or the pressure from high pressure to low pressure, auto refrigeration happens and you have low temperatures. So if you repressurize again, you have conditions that can promote cracking due to low temperature conditions. So this is all governed by ASME code if you use G20. The ASME code provides to ensure that the steel is good enough, you have to impact test it to make for certain impact testing to make sure that the material is tough enough at design conditions. And the impact testing requirement is spelled out by these figures. And if you are below the curve, I show the curve, you don't have to impact test. If you are above the curve, you have to impact test. If you are below the curve, you have to impact test. Of course, impact testing means money, and people try to avoid it because it costs money during fabrication. And this there is if you like to reduce to avoid heat impact testing, you can heat treat if it is not required by code. So that will allow you to use the material without impact testing. And there are other, if you're working with very low stress levels in the components, you can still lower your minimum design temperature. You can work with non-impact tested materials. This is from the code UCS 66, which shows each line shows group of materials. This is like, for example, structural steels. This one like carbon steel, killed carbon steel, but not normalized. This one for carbon steel, killed steel. So if you have a thickness, like say 3 inches thick component, and your design temperature is -20, and you're here, so you have to impact test your material, make sure this material is tough enough, otherwise you have to use some other alloys. So you start with carbon steel, and if you impact test, it became like low temperature carbon steel. And if still is no good, then you have to use low nickel alloy steels. And in worst case, you go to stainless steel. So this is a sequence of material selection due to low temperature environment. Of course, to avoid, if you are working with low stress, actual stress, and if the ratio of the stress divided by allowable stress for the design conditions, say you are 0.6, and so you get a factor, you can go 40 degrees below this curve. If you imagine, you can make a curve 40 degrees parallel to this one, so you are shifting this curve down, and if your condition is here and the new curve is like that, you don't have to impact this. So this is only for application where you have low stress values, but this can happen for nozzle components, but for pressure vessels sometimes this doesn't work. So this low temperature is very important for us, and it is we use a lot of low temperature materials in Alaska, and ethylene plants, ammonia plants, and LPG plants. You need to be careful with that. Gaseous oxygen, it is a very dangerous material to handle, and it ended up with a lot of accidents that killed people, injured people. And gaseous oxygen is defined if you have more than 90% oxygen in the gas. Once you have 90% of oxygen, then you have to be careful of material selection for it. Because oxygen in this concentration can burn metal like wood. It can burn steel, it can burn stainless steel, and it doesn't take time to burn violently these materials. So there's ways to avoid that, to reduce your velocities. You have to reduce your pressure drops. You have to use materials that is resistant to oxygen burning. You have to remove all contaminants. If you have even dust or oil inside the equipment before using oxygen, these are like a sparking, like a igniter for oxygen to start reaction and burn the whole thing. So you have to clean the system from oil, grease, dust, any organic matter that can cause ignition, and this will promote the ignition of the rest of the equipment. You have to proper design to have smooth surfaces. You don't want to have friction. You have to avoid edges that cause turbulence. And you have to avoid velocities, turbulence, and increase in temperature. There are charts that help material selection, and this is one I picked from one of our customers. And it is a function of pressure of the system and the velocity. And in this zone, you can use carbon steel with stainless steel trim. In this case, you have to use stainless steel in this area. And above that, you have to use nickel alloy. Nickel is known to be resistant to oxygen, gaseous oxygen. And Monel is a very famous material to use in gaseous oxygen to avoid burning. It doesn't burn in oxygen. So this is a curve that we use to select materials. Piping, in this case, valves, we use the nickel trim, Monel trim, for this purpose, because in the trim you have turbulence, and if you don't use Monel, you might start igniting the trim, and this will ignite the whole thing. Now we know the basis of how we select, the basis of what is happening and how to estimate corrosion rate and what is possibility of failures and corrosion mechanism. Now we have a new unit, we need to select materials for it. And we get from the process people the process flow diagrams, and we get from them the heat and material balance, and we start estimating what is the corrosion rate. If you have H2S, what is the partial pressure of H2S? Does it have hydrogen, no hydrogen, etc.? And then we start estimating corrosion rate based on the curves I gave you before. And based on that, you start selecting materials. Then we prepare material selection diagram, which is a copy of the PFDs, except we indicate materials of construction on the material selection diagram instead of other process parameters. We try to leave the temperature, pressure, so give you where are we. And we give indication. I'll show the example of material selection later on. And we give a legend to explain what is each symbol means. We indicate special material requirements. For example, if you have wet H2S, we indicate heat treatment. We indicate that material should be tested for heat resistance or some other special requirements. Maximum velocities to avoid corrosion, erosion in amine series, we indicate that. And these material diagrams are very important document for any project. They are internally squad checked and approved finally by the client for implementation. Here is an example of a material selection diagram we did for a North American job. And this is for, I forgot what it was for. looks like a sour water system, sour water stripper, I think. And you have the equipment. We give the material selection. I'll show in detail below each equipment what materials to use, corrosion allowance, etc. And for piping, we give designation on each line. And in the key here, we give explain what it is. And here in the notes, we give the requirements, special requirements. So this is a typical example of material selection diagram. By just one look, you can tell where we have carbon steel, where we have stainless steel, what special requirements, stress sleeve, no stress sleeve. So it's a very, very useful tool for project material selection, preparing specifications for data sheets and everything else. This is an enlargement to one section of that, where we have this vessel and this piping. It looks like it is here. The key says it is 304 stainless steel, 0 corrosion allowance. And here you can say there is a carbon steel with 3.2 millimeter corrosion allowance, but it is sour service. So you have to apply some requirements for sour service. What other? Here this part, it is like, looks like in here, it is a stainless steel 316, 0 corrosion allowance for chemical injection type piping. For pumps, we indicate the API, if it is API pump, say API S8, which is carbon steel casing, and 316 stainless steel impeller. Here this API A8, which is all stainless steel, 316 stainless steel pump, and this one S1, which is carbon steel casing and cast iron impeller. And here for equipment, we indicate what equipment is carbon steel with cladding, this vessel, and we'll give the internal materials. If there's internal, it should be stainless steel in this case. So it's very useful, a very concise diagram, give you a lot of information that is used by everybody to buy equipment and prepare piping. So we're finished with material selection. Now we try, sometimes some clients ask us to prepare corrosion control program or proposal, and we try to control their corrosion. And we control corrosion, of course, by proper material selection. We control corrosion by proper material identification. A lot of materials like carbon steel and low alloy steel, they look alike when you look at them. And by mistake, fabricators can use carbon steel where you need chrome moly steel. And in order to avoid that, or the fabricated item, once it is delivered, you have to perform positive material identification. It is an instrument that go over the metal and welds and identify to say, oh, this is it tells you it is 5 chrome or just carbon steel. It doesn't tell you it's carbon steel, but tells you 5 chrome or stainless steel. If it is meet specification, so this equipment is meet, they use the proper material specified. If it is not, then you have to replace it. Otherwise, you end up with the catastrophe later on if you put it in service. And this was required based on a lot of incidents that fires and leaks and people die because they used carbon steel where you have to use 5 chrome, and you end up with a corrosion, leak, and fire and disasters. So this tool is very important to avoid. And if you use the proper material, actually you're controlling corrosion. We try to avoid corrosion by avoiding dead legs and spots, free drainage of equipment. Try to avoid galvanic cells because it generates corrosion. If you have to have galvanic cell, maybe you have to put isolating gaskets, electrical isolation between the noble material and the less noble material. And these kits are available in the market. We can use inhibitors where it is applicable. We can use water injection, as I mentioned, and above the reactor effluent cooler. Inhibitors also, there's a barrier for corrosion, and it is the barrier between the service environment and the metal. We use cladding, which is a high alloy steel on top of carbon steel or weld overlay. that also is a high stainless steel type materials, and this is like again barrier, solid barrier between the low material like carbon steel and the environment using that. Use non-metallic lining like rubber lining, it is used frequently in some vessels. We use non-metallic materials of construction like high density polyethylene or polypropylene or Teflon. We use cathodic protection. It is a system I'll describe later on to, as I said, the corrosion, it is an electrochemical process, and if you make everything is cathode, the cathode doesn't corrode, the anode corrodes. So if you make the whole structure is a cathode, then it doesn't corrode, so you're okay. We use painting and coatings and wrappings on equipment internally, externally. Of course, painting is internal and coating is internal. Wrapping for underground piping. We use, this is also a big item for corrosion prevention. Reinhardt will talk about that. We use refractory for high temperature isolation. If you have a very high temperature, use refractory and heaters, reaction furnaces and sulfur units. We use acid resistant cements and sulfur pits to prevent corrosion of those items. We use galvanizing for atmospheric corrosion prevention, electroplating on some of the components of valves, etc. We'll now talk about one of those items, cathodic protection. Cathodic protection utilizes the flow of direct current to interfere with the activity of electrochemical cell responsible for corrosion. This is achieved by connecting a metal to be protected to a more negative terminal of direct current source or more negative metal of the galvanic series. As such, the entire surface being protected become cathode. This means doesn't corrode. Cathodic protection may be applied for underground piping, pipelines, other metals, internal surfaces of vessels, tanks, cooling water system, heat exchanger equipment handling cooling water, structures and seawater service, harbors, jetties, sublines, concrete reinforcing. Even the reinforcing bars in concrete, they suffer a lot of corrosion. If you connect this reinforcing bars to cathodic protection system, you can protect the reinforcing bars. A lot of time you see in the streets reinforcing bars and freeways, they corrode and becomes useless. So you have to replace. If you have cathodic protection, this protects it. Cathodic protection, we have a consultant with us. He's ex-Parsons person. He's working with us. He can design for us any cathodic protection system we want. Once he designs it, he goes to electrical engineering to make the detail of it. Here is again the galvanic cell, and this is this material, magnesium, zinc. They are used as a sacrificial anodes for cathodic protection. Here is just a crude example of how it works. Here is a pipe underground, and it is protected by sacrificial anode, which corrodes into the soil, but it gives up its electrons to the metal, to the cathode in this case, becomes a cathode. So it doesn't corrode, and the circuit goes through the soil. The soil is anyway, it's considered to be electrolyte. And instead of using sacrificial anode, can be zinc or magnesium, which has a less noble than the carbon steel, and it acts as a sacrificial anode. Or you can use battery or a rectifier to give you the electrons to the structure, and the other part goes to another. You put a node of different material like IR silicon anode, and which is connected to the battery and or rectifier, and the circuit is completed through giving the current to the electrons to the, actually the electron goes this way, the current goes the other way. It is the opposite direction. The electron goes here to give protection to the cathode, and continues here, and the circuit goes through the soil. So this is the principle of cathodic protection using, in this case, cathodic sacrificial anode. Yes, they call it impressed current. You are impressing current to the structure. Okay. Corrosion inhibitors, they are a film-forming type material that it has a polarity and like a small magnet, and I think the positive part is the polar. It sticks to the wall of the pipe or the vessel and form a film on the wall. So it is a barrier between the process and the metal. So it gives protection. And of course, you have to build up this film when you start up the unit, and then you have to maintain it because this film might erode from the process. So you have to keep injecting inhibitor to maintain this film. Selection of inhibitors, there are thousands or hundreds of these inhibitors, and a lot of chemical companies produce them. Then you have to get their experience, you have their own client experience to select them, and also there is some lab testing can be done to identify which one is more suitable to your service. It can avoid using alloys, stainless steels. You can use carbon steel when you use corrosion inhibitors, of course, if it is proven to be successful. It is used extensively, like in North Slope in CO2 corrosion prevention. It is injected with produced water. It is injected with the crude itself, so it gives protection. And in such cases, you can use carbon steel. Of course, another way of controlling corrosion, painting and coatings, and Reinhard will go and talk about this in detail in the next session, and after I finish. So these are the main topics of corrosion prevention. Corrosion monitoring. So you established your material selection, you established your corrosion control system. Now you like to see if it is working or not working. Because if it is not working, what to do and correct it as a prevention, because things can go wrong. So one way of doing it is using ultrasonic thickness measurement. This is an ultrasonic thickness measurement. It is an instrument which is usually portable. You can go around the equipment and measure the wall thickness of the piping and equipment, and you have a log of it. You measure it when it is new, and then you measure it after 1 year and see what is the thickness is. The difference means metal loss. You can calculate that, the corrosion rate, and you see it is really corroding or it is not corroding, and take necessary action. There is an API documents about how to make this measurement for vessels, fired heaters, piping, tanks. It is given all in API recommended practice 572, 573, 574, 575. Give you a good idea how to handle it, and it is useful for, not for us, for operating people. We can use the chemical analysis of process streams. If you check your water from separators and you notice there is a lot of low pH, so you know there is a corrosion problem. No, you can, and then you check for the iron content. The iron content in this water gives you indication of corrosion activity. And if you usually have, for example, 1 ppm iron, you notice it became 5 ppm. So you have a problem. Then check your inhibitor injection. Maybe it is not working, or maybe the pump is not working, or the dosage of an inhibitor is not enough, then you have to increase. Or some upset condition in the process created this situation. So this chemical analysis of water, very important. It tells you also how much H2S you have in the water. Is it highly corrosive or not? How much chlorides in it? If you have cracking in stainless steel, or you have chlorides in this system, low pH, so you have an environment that causes cracking. So this chemical analysis of water process streams is very useful. Corrosion monitoring, you can use weight loss corrosion cones. Weight loss corrosion cones, pieces of metal like this, like these strips, like 3 inches long, 1 inch wide, ½ inch wide. You insert it inside the pipe using a probe or a handle, and it goes in the stream, and you insert it. Before you insert it, you clean it, you weigh it, and see how many grams it has, how many ounces or grams of metal. You insert it, and then after 1 year or 6 months, you remove it and clean it, remove the scale, look at it, see what corrosion happened, and then weight again. And the difference in weight is a function of corrosion rate. And if you know the surface area and the weight loss, you know the density of steel, then you can correlate that to make calculation and give you corrosion rate. So you can monitor the corrosion in the system by using corrosion couplings. They are different forms, some of them round, some of them straight. And they have a handle which they can insert them on stream, can insert them through a handle, go this system, and then you can also remove them on stream. They can be handled. You can insert them, you can remove them on stream without shutting down the system. A useful tool to monitor corrosion.